So the title of the talk today is Improved Space Charge Limited Emission Algorithm in VSim, and I'm Peter Stoltz. This talk was put together with a bunch of collaborators, especially John Lugansland. He's really the driver behind this whole thing. And John works at a company called Confluent Sciences now. He used to be a professor at Michigan State. He's really well known in this space charge limited emission world. If you look up the references on this stuff, you know, he's on 90% of them. So it was good to have him on board for this work. Andrew Chapp did a lot of the actual coding on this for getting this algorithm into VSim. David Smith and John Carey. In fact, I think you hear from David later this morning. Yeah, David has worked on these things for a long time. John Carey, I don't know what that guy does. The good news is that this is in VSim 11 and will be available when VSim 11 is released. Okay. Well, I guess I do. How's that? All right. Okay, so the first thing is handily, just by sheer coincidence, this work just got published just this month. So the details, if you're really interested in this stuff, you can read this publication. It is open. There's no journal subscription required. So you just go to the Phys Plasmas website and search for that title there, and it'll come up. So yeah, the paper has far more detail than I'm going to put in the talk today. So you can reference that if you want to learn more. I have this at the end of the talk too. There's a little slide there, so you'll be reminded at the end if you want to jot that down. Okay, so I'll tell the story. I'll tell the story this way. I'll talk about the actual device that we set out to model. And then we're going to take a giant detour down the road of verifying and validating our algorithm. And then we'll come back to this device. So I'm starting at the end. And the end is that the Navy came to us and suggested that we might be good for simulating these high power RF devices. They get called directed energy devices, RF devices. And these things, they want them to operate at very high power. These are maybe for radar, maybe for signal jamming, electronic warfare, that kind of thing, but you want lots of power out of these devices. And the one that you're looking at there is called a MILO. MILO stands for magnetically insulated line oscillator. And the actual device is actually just right there, just that little bit of it right there. Everything behind it there in the blue is the power supply. There's an antenna on the front so that when you generate your directed energy, you can broadcast it. There's some pumps because you can't do physics without pumps. But yeah, so there's this device, right? It's called a MILO. It converts DC energy into RF energy. And the way it does that is through having an electron beam that interacts with a structure. We're going to get into all the details of that later in the talk. But the important part is that you want these things to be at the highest possible power. That typically means the highest possible current. And sometimes simulating really high currents in a PIC code can be challenging for reasons we'll get into. So anyway, that's the end of the story. The end of the story is the Navy wants us to do this, and we set out to do it, but we wanted to make sure that we could simulate these really high current beams in a PIC code. And so to do that, we said, well, let's make sure it's working by stepping back and looking at the very simplest problem that we could, just two parallel plates. So over here, this little color contour plot over here, I set up in VSim just 2 parallel plates and I applied a potential between them. So you're looking at the potential over there. Low potential down here, high potential up here on the top. And if there's no current at all in my system, you just get a straight line. If you take a line out from the bottom here to the top, blue to red, it would look like that. No current at all, straight line. And then as current starts to flow, so maybe you inject some electrons down here, they go towards the top. As current starts to flow, those electrons make their own electric field. That changes the potential a little bit. And if you can tell, this line is starting to bend a little bit. And if you get all the way to the point where there's so much current emitted in your system that the field at the surface, d phi dx, goes to 0, that's what we call the space charge limit. You actually can't emit more current than that. It would get pushed back into the cathode. And so this potential here has a curve to it. And in 1D, there's a way just to write down an expression for that. You can work out a steady state value for how much current you can emit given a voltage and a gap distance, d. And sometimes in this talk, I'll use SCL, which stands for a space charge limit. And sometimes I'll say CL, which stands for Child-Langmuir, which is the, that's the name of the equation that describes the space charge limit. And in 1D steady state, they're the same. I'll kind of use them interchangeably, but yeah, there's a little bit of nomenclature. So yeah, quick interlude before we go with more physics. 1D parallel plate, that's too easy, right? Who runs in parallel plate? Nobody, right? But cylindrical geometry, that's when things get more interesting. And the person who actually worked out the solution for cylindrical geometry is this woman named Katherine Blodgett, and kind of an interesting biography for her. She was the first woman to get a PhD in physics from Cambridge in England, and she was the first woman physicist hired by GE Research back in the 20s. And she's the one that worked out the generalization of changing that geometry from 1D planar to cylindrical, and she did spherical as well. So at the end of the talk, when we go back to that MILO, which is a cylindrical system, we'll actually be talking about the Langmuir-Blodgett equation instead of the Child-Langmuir equation. And yeah, so that's Katherine Blodgett. So just a small historical interlude there. Okay, back to physics. All right, so back to this parallel plate problem that we'd set up. And so, we kind of have it all figured out, right? So there's this system here. We have an equation that we know describes it. And, back 8-10 years ago, I helped design the very first implementation of how we were going to do these high current emissions in VSim. And, I consider my specialty the wrong, implementing the absolute wrong way to do things. I am incredibly talented at that. So I'll tell you what we did, right? So you look at that equation and it seems so easy, right? Because your voltage, that's whatever you're applying. Your gap distance, that's how you set up your problem. It seems like you just plug in those values, right? It tells you exactly how much current to emit, right? No problem. So first time step, yeah, you just do it. You do exactly what this equation says. Well, the problem comes on the second time step because this voltage and this distance don't change, but now you've already got current in there. So now what do? Emit nothing, maybe? Okay, so now you emit nothing. Or maybe you try to keep track of how much current you've already got in there, and then you want to emit just a little bit more. It starts to get complicated. And by the third time step, you realize, well, you've actually put in too much and some current's going the wrong way, and now you're starting to panic. What do I do now? Do I include the current going the wrong way? V and D still haven't changed. Things are going haywire. So that was our first implementation. And, you know, I had all kinds of ways to kind of get around these problems with the system, you know, oscillating, and one time step you put in current, the next you don't, and all these things. So I had these fudge factors I would use to reduce the current I was emitting, and sometimes I would scale it by the time step, but that's a disaster because the time step changes with the cell size. So, you know, this is what we had, and I had learned to work with it. But John Lugensland, you know, the second author on this work, and the guy I said is really the expert, he took one look at this and he said, "You're crazy, right? There's no way we're using this." So John Lugensland was really the inspiration here, and he said there's definitely a better way to do this, right? And the better way, well, one thing you'll notice is that I've rewritten this equation a little bit. It's not in terms of the voltage anymore. How about that, right? It's in terms of the electric field. So you just replace the voltage by E times D, right? And you can write this in terms of the electric field. And so we rewrote it this way, and now you're looking at the same plot over here, but I've taken just one little zone, just the one zone right next to the emission surface, and I've blown it up, right? So now you're looking at just that one zone there. And what we do is we say, well, what if the space charge limit really applies just to that first zone, not to the whole system? It'll eventually end up being across the whole system, but let's just start with the first zone. And so you use the E that's in that first zone, and you use the distance that is one cell across. Otherwise, it's the same formula we were using before. And what's nice about this is this electric field right near the surface will start to change, and we saw that before. It's actually trying to go to zero, in fact, near the surface. And so that will change almost right away when we start injecting current, and there'll be this nice self-consistent feedback. So this is the new approach, and this is what's in VSim 11 now, is this new approach. Now, if you're paying close attention there, there's something that looks a little strange. And the thing that looks a little strange is that this current that I'm trying to emit actually depends on our grid size. That seems a tiny bit weird, right? Because that means if you add better resolution and your cell size gets smaller, the current's going to go up, and in fact, it's going to diverge. Doesn't seem great. And you can look in the publication and read all the mathematical details about this. It turns out, right, that like I said, this electric field is trying to go to zero in the space charge limit. So remember that right near the emission surface, that's where in the true space charge limit, you'll get zero electric field. So this numerator is actually trying to go to zero at the same time as you reduce your resolution, the denominator goes to zero. You can look at the math in the paper, and the two actually cancel out exactly. And so that emission current stays constant as you increase the resolution. So that's good. That's much more physical. Okay, so here's our first test, right? So we put in that new algorithm, and we're doing our first test now. So we're going to emit some electrons off this surface. We're going to watch them move to this surface over here. And here are a couple time snapshots, and let's talk about how we're scaling things on these plots, because we're going to see this a lot. Okay, so on the y-axis, for almost the rest of this talk, you're going to see current density, current density, and it's going to be scaled to that Child-Langmuir estimate, the theoretical estimate. So 1 is good, right? 1 means you're getting the correct value, at least in planar geometries. Okay, so that's going to be our y-axis for most of the plots in the talk. The x-axis is the time, so I'm letting this system evolve, hopefully to a steady state. And the time I'm scaling by what I call the transit time. The transit time is just the time it would take one single electron to get from the bottom to the top. So it's basically the crossing time. It's a good measure of how long, how much of a chance the system's had to get into steady state. So yeah, so that's the time scale, and you'll see a lot of these plots scaled by that transit time. All right, so a couple things. Let's talk about this plot. So there's 3 curves plotted. Maybe one of them is hard to see here, but there's 3 curves plotted there. They're labeled up here. One is the emitted current. It's kind of this dark green line. One is the current that tries to leave the cathode. There's too much space charge and it gets pushed back. That's that light blue curve. And the last curve is the current that makes it all the way across, makes it to the other side, and that's the dark blue curve. So we would really like the dark blue curve to be at 1, and we would like the green curve to be at 1 as well. And ideally, we want the light blue curve to be at 0. That's probably our most efficient algorithm. Yeah, and you can see what happens, right, is that at the very beginning, the system tries to over emit for a little bit. That self-corrects because the electric field in that first cell actually turns around. So that's good. So this problem of over emission self-corrects, and it does so rather quickly compared to a transit time. A lot of current initially gets pushed back to the cathode. That's the light blue curve, but that actually stops by about a half a transit time. And things settle in actually pretty nicely, right? There's a little bit of a spike that's related at the anode that's related to that initial surge of particles, but that goes away. And by 2, for sure by 3 transit times, you're in a nice steady state. All right, so that actually seems to be working pretty well. No crazy oscillations, not too much current being pushed back to the cathode, which is just, you know, kind of a sign of an inefficient algorithm. So no, this looks really good, super promising. And yeah, now I'm going to talk about all the different ways we tried to torture this 1D test into failing. We tried a bunch of different things just to see how robust it was. So let's go through a few of those. Oh yeah, sorry. One thing I did want to mention is, you know, we talked about how if you increase the resolution, you'd like to get a better answer. And so what I'm plotting here, if I go back one slide, you know, it turns out if you really zoom in, this answer isn't quite 1. It's off by a small amount. And the question is, if you add more zones to your simulation, what happens to that error? So here I'm plotting on the y-axis the relative error. That's my measured current compared to the analytic value divided by the analytic value. And on the x-axis, I'm just increasing the number of zones in my simulation. And it's a log-log plot, and it converges like the 2/3 power. And that makes sense because you can go look at the publication, but it turns out that that's how the electron density scales, is as the 2/3 power of the position across the gap. So that made good sense, and it means that as you increase your resolution, you actually do get a more accurate answer. So that's good. So that was a good check, and we were happy with that. Okay, so the first thing we tried after being happy with the 1D test, we said, well, what happens if we have current going 2 ways, not just one way, but 2 ways? And one case where that might happen, right, is if you have secondary electron emission. So that means that maybe your anode is not a perfect absorber. So you could get some emission off the anode due to secondary electrons. And sometimes there is a small fraction of the secondary electron emission that is a purely elastic scatter. And so I've just taken that to the extreme in this case. I've said, let's let every electron be a purely elastic scatter. And so that's the case that we're looking at now. In that case, right, you're going to have current going backwards and forwards at the same time. So current going from the top to the bottom and the bottom to the top. And so you might expect that there would be about half as much current because now there's twice as much charge. There's some going each direction. So we kind of think there might be about half the child length value in this case. I'll tell you a little bit about these plots, right? So over here, you're looking at the velocity. So positive velocity means you're going from the bottom to the top. Negative velocity means you're going from the top to the bottom. I've just scaled it to the maximum velocity. Yeah, so there are some particles going from the cathode to the anode. They get reflected in this elastic reflection way, like a secondary electron emission, and then they go back from the anode to the cathode. So that's what we've set up here. And what you see over here on the right is that you do get about half of the child Langmuir valued current. It's not quite perfect. And in fact, it's a little bit too high, and that's because you're actually pushing a little bit of current back to the cathode. So this light blue value minus this dark blue value would be 0.5. And the reason you end up with a little bit of current getting pushed back to the cathode is because of the finite transit time. Like the reflected electrons aren't there immediately, right? They take a little bit of time to get there, a few transit times. And so during that time, you set up a virtual cathode. And so that's the reason for that. But we were happy with that result. It showed that the algorithm is pretty robust. It can handle current going in both directions at the same time. So again, we were happy with that. Oh yeah. So another way that we tried to test this 1D parallel plate case is we said, well, so far we've always just assumed the voltage is there at time 0, right? At time 0, there was the full voltage across the gap. But in a lot of cases, that's not going to be the case, right? In a lot of cases, you'll want to start your simulation and the voltage will ramp, change with time, maybe reach some steady state value. So there's a time-dependent voltage effect, and you know what's that going to do to our system? So that was kind of our next test. And yeah, so there's a new curve here on these plots, and the new curve here is the green curve now represents the voltage. So so again, the time is compared to the transit time, and now the green curve shows you the voltage compared to its final value over time. And it turns out, right, that if you ramp your voltage very quickly, you will see an effect on the emitted current off the cathode. Sometimes that can spike a little bit high because you're ramping the voltage quickly compared to a transit time. And the cathode takes a little bit of time to respond. But eventually, after, again, 2 to 3 transit times, it settles in nicely and you get a nice steady value. In fact, you can modify this inductive spike here by just changing your voltage. So over here, we've ramped it a little more gently. So you can kind of tell that this one's at its peak by about 1, and this one's not at its actual peak till about 2 transit times. So it's a slower voltage rise, and we were able to get rid of that inductive spike entirely. So, so yeah, it looked again like this algorithm is behaving really well. It can handle kind of current heading both directions. It can handle time-dependent voltages. So yeah, we're really pleased with the 1D test so far. All right, let's see. Okay, so now we're going to try to make things interesting. You know, 1D, everything works in 1D, right? Things don't get interesting until you try 2D. So there's a well-known test problem in the literature, and that's just a finite width emission patch. So it's the same setup actually, right? It's still just a parallel plate system with a constant voltage, but now instead of letting the electrons emit off the entire cathode, I'm just going to pick a region, width W, and emit from just that region. So now there's going to be edge effects. It's not a purely 1D system. And there are no necessarily analytic answers here, like we had before, but there are, this test problem has been published by a number of folks, and so we have things we can compare to code. But one thing I wanted to check right away in this system is that, you know, if you pick the middle of the emission region and you go cathode to anode, you kind of expect that it's going to behave the same as the 1D case, you know, especially if W is wide enough. You're like, you know, this is far away from the edges. It should really just be 1D if you look straight down the center here. So that was the first thing we checked, and that's over here on the right, and it's what we expected, right? So we ran this system. This is the current at the anode as a function of transit time. And again, after 1 or 2 transit times, it settles in nicely. It looked like the 1D child linear value. We don't necessarily expect it's going to do that on the edges, but in the middle, it did. So that was a good check. Yeah, now things get fun. Now I get to use color in my plots. All right, so here's my finite width emission region. And we're going to watch the electrons go from the cathode to the anode. And yeah, kind of the first thing you notice is that there are these like little horns on the edges, right? And you can really see them over here. You get big enhancements at the edge. If you take a line out of the current density spatially, so the x-axis now here is space. So I started in the middle. 0 is actually the middle of the emission region to the edge. And you look at what the current density is doing. Well, in the middle, it's the child linear value. That's what we saw on the previous slide. But on the edges, it's increased quite a bit. So you can get a factor of 3 enhancement on the edges. And that factor of 3 enhancement is what people have seen previously. There's this reference down here from just about 20 years ago now. In a different particle and cell code where they saw the same factor of 3 enhancement for this problem. You know, like I said, you see John Lugansland's name on these, all these space charge limited emission papers. So there he is down there 20 years ago working on this problem even back then. Yeah, okay, so the 2D case looked great. So yeah, okay, so we've tested it in 1D, we've tested it in 2D, and now we're finally ready to get back to the real problem we were trying to solve, which is this magnetically insulated line oscillator, which I said was an RF source. It converts DC power to RF power, and it does it through an electron beam interacting with a metallic structure, and we'll talk about all the details of that. I show a picture of it here in VSim. So if you remember back on the very first slide, I showed that MILO was just a little hunk of metal. You know, it's about 10, 20, 30 centimeters long. It's about, you know, maybe 10 centimeters in diameter. And so this is a picture of it in VSim. The inner coax here is the cathode. The outer coax is the anode. So now the electrons are going to flow inside to outside. You can see a little bit of kind of like rib structure out here, like veins. And we'll talk more about that, but that's the whole secret sauce to these MILOs. That's why they convert DC to RF. But one thing I wanted to mention first is that suddenly our emission surfaces are not going to align with the grid. And if you have done PIC simulation a lot in your life, that you know that that's challenging. If you have not done PIC simulation, yeah, this is one thing that VSim is really known for, is it's got a lot of names, but here I called it an embedded boundary capability. So our grids in VSim look like rectangles, squares, but the boundaries themselves that we treat do not have to follow those squares. So that's what we call an embedded boundary, complex geometry. It's got a lot of names. And so I show an example here of what, you know, a curved cathode might look like in VSim. And so now our electrons might be going kind of to the side. We use the same algorithm that we used before. It just takes advantage of the fact that these corner electric fields might be inside the cathode, inside the metal, and so they'll be zero. And it all is taken care of naturally. And we can use the same algorithm we've used previously, and it's going to work in these kind of cut cell geometries, which is great. It wasn't obvious that was true, but it turned out to work. Okay, so let's talk a little more about how the MILO works. So I've taken a sectional slice now. So this is the longitudinal direction down here, and like I said, they're 20 to 30 centimeters long, and like total something like 10 centimeters in diameter, and the inner coax is the cathode. The outer structure is the anode. We're going to apply a voltage from cathode to anode on the input side. That's just going to be a DC pulse. And we're going to look at what happens out here, where we hope to see some RF. We hope that the voltage out there is varying with time. And the way that happens is that the electrons that are trying to go from cathode to anode are going to see this kind of tooth-like structure here that's very carefully designed. This gap spacing between the teeth is critical. And if you're an RF device designer, this is what you spend your time doing, is optimizing things like that. The difference in height between the first two of these veins and the others is also critical, and there's more detail in that. John Lugansland put this one together for us. But yeah, so that's how the device is going to work. Yeah, I think I said everything I need to say there. Oh, I will mention that the drive voltages are typically really high. Like I said, you're trying to get as much power out of this thing as you can. So we're talking about 500 kilovolts on the input side. I think you remember the picture at the beginning. I can go back to it real quick. It's they have an entire bank of capacitors. So this is the input DC voltage back here, right? I mean, the pulsed power is actually the biggest part of the entire device. So, these are high power devices and they take a lot of input DC power. Yeah, so it's going to be 500 kilovolt input. So that might remind you that that's about the rest mass of the electron. So these are going to be relativistic devices as well. Okay, on we go. Right. Okay, a lot to look at on this slide, but basically what we're doing is we're applying that voltage on the input side. This side is going to be my input side. We're going to apply that voltage. We're going to let the electrons flow from cathode to anode. It turns out that there's so much current that they create their own magnetic field, and the V cross B forces turn out to be as big as the electric forces. And so you see that it tries, most of the electrons try to stay near the cathode. So the applied voltage is over here in light blue. This is, the y-axis is kilovolts, so we're at about 500, not quite 480, I think we ended up at. The time now is not normalized, it's in actual units, that's nanoseconds. In the pulsed power world, that's, that's the typical unit. If you get 100 nanoseconds out of something in the pulsed power world, you're doing well. So, so yeah, the units here are in nanoseconds. In the middle plots, you're looking at the electrons, and they're colored by their velocity. So red is high velocity and green is low velocity. And then it's a little hard to tell. The color plots are great because you get to see kind of what they're doing, but it was a little hard to see kind of the structure of the electron beam. So again, I took a slice, a longitudinal. So this is longitude again, and we just look side on at what's going on. And I plotted the electrons now all the same color. And you can see, it's a little hard to see, that the electrons are actually running up inside those veins. That's great. That means we're getting good interaction between our input voltage and our beam. You can see structure to the beam out here. Again, that is great. That means we're getting good interaction and we can expect some RF power. So this all looked really good. Let's talk about the total current that we were getting. Again, it's high voltage, 500 kilovolts. And so you expect a lot of current, kiloamps of current, and that's not unexpected in devices like this. And if you look at the current that came off the cathode and the current that makes it to the anode, we were getting about 50 kilovolts in each, and we ran it out about 20, 25 nanoseconds. And that value, if you look at the Langmuir-Blodgett equation, remember Blodgett corrected the 1D parallel plate to be coaxial. If you look at the Langmuir-Blodgett equation and correct it a little bit for relativistic effects, she did the non-relativistic case. Yeah, you do get about 50 kiloamps of current as the answer. So this is all good. All right, and so so what happens, right? So again, on this plot over here, I am plotting voltage. The light blue curve is that 500 kilovolts of input voltage, and the dark blue curve now is the output voltage. It's the voltage on this side. So this is what's coming out after interacting with the electron beam. It's what we're hoping is RF modulated. And you can see already, it's looking really good. This arrow, it's not pointing incorrectly. I measured this signal inside one of those teeth. And that's just because that's where it's easiest to really see the effect of this RF oscillation. So in between two of these teeth here, I just looked at the voltage and it's oscillating like that. And it's as high as the input voltage. So we were seeing voltage oscillations, RF voltage oscillations on the order of 500 kilovolts amplitude. So that's great. It means it's really working well. If you take an FFT of that dark blue signal, it looks like this. So a main frequency pops out right away, 13 gigahertz. The way you control that is with these teeth spacing, with the size of the device. That's how you determine the frequency of your output RF. But 13 gigahertz matched really well with previous results. So there was an experimental device in by a group out of China where they measured some of these things experimentally, and 13 gigahertz was the expected frequency for this device, and so that was great to see. If you look way out here, we're actually even seeing a harmonic, which is another good sign. It means we're getting really strong interaction between our electron beam and our RF. So that's another good thing to see. Okay. So the bottom line is that our new emission algorithm is working really well. It's well tested. We even got to apply it to a real device. And that kind of wraps it up. It's all published in that paper there. And I'll take any questions.
All right, one moment, everyone. It looks like we just lost Peter for a second.
Oh no, I'm here. I'm here, and I see a question about the shape of the inner coax. Could it be cone-shaped? So I guess you're asking, you know, that inner coax is actually aligned with the grid in Z. I mean, it certainly could be, yeah, any shape of coax, of inner coax. Yep. Oh, instead of the ribs being different. Okay, this is a great question. I guess you all can't, the rest of the audience can't see it, so I'll repeat the question again. So one of the audience members is asking, if I back up a couple slides. Yeah, so let's back up even one more. Right, this slide. So there was a question about, I said that these teeth, these veins, the fact that they're different length can actually be important. And so one of the audience members asked, what if you just change the cathode shape, right? You could make the cathode bigger out here and ramp it down to decrease the distance. Yeah, that is a great question, and I don't know. I don't know if John Lugensland is dialed in. He would know. Yeah, no, that's a great question and a great idea. I've never really thought about it. Oh, Bob Terry. Oh, I see a couple more questions now, actually. Can you generalize this to include emission from ellipsoidal needles to the Richardson-Dushman limit? Yeah, so I guess you're asking about kind of details of electric field enhancement, and that I guess would be captured if the geometry captures it. You know, this emitter does not include any Richardson-Dushman or Fowler-Nordheim effects specifically in it. Yeah, have to think about that one some more. I mean, certainly, so the question is, you know, there are these other equations, Richardson and Dushman and Fowler and Nordheim, that kind of account for almost surface effects and quantum effects on the surfaces. They include things like tunneling. And yeah, I have never, we have not tested our emitter in that limit. But thanks, Bob, for that question. Yeah, so way back when I was doing the 2D, this case right here, Seth writes asked a really good question. Why does the beam seem to be going so straight across and not spreading out at all? Yeah, that's a great question. We actually put a magnetic field on in the vertical direction to kind of hold it hold it in place. Yeah, it's described in the paper. The details of that are described in the paper. Yeah, that's why it looks so collimated there, because there is a longitudinal magnetic field to make that happen. And that's just because it makes it easier for comparison's sake, right? Instead of having current going way over here that you have to kind of collect and decide whether it came from the edge, you can just see right away which particles came from the edge. That is a great question. Thanks for asking that. Ming-Che Lin asked, do you think this will work for beam with an initial velocity? That's another great question. Yeah, I do. I don't see any reason why not. So we would solve a slightly different equation than the simple Child-Langmuir equation. But yeah, it should work. Haven't done that yet.